Okay, let's continue with our idealization. So now this is an idealization of our single degree of freedom system. So for this one, now we try to allow the structure to move only in a single or one direction. So the assumption with this one is that its columns is massless. It is vertically, infinity rigid vertically, rigid in the vertical direction, but flexible in the lateral or flexible laterally or lateral direction. So this is our assumption in this single degree of freedom system. Aside, the columns has what? The columns has a lateral stiffness K. So what is this lateral stiffness K? If you remember now in your dynamics of rigid bodies, we have a restoring force F is equal to negative Kx. So you theta as a behavior of your spring. So if you have a spring in its initial condition, and then if you add a mass on it, symmetrical spring, si spring is mainat or will be displaced to a certain distance. And that displacement, that will be the our x. And then you'll have your elastic restoring force. Also here, the considerations upon structure is that the columns is flexible in the lateral direction, but it has a lateral stiffness K. So pasabot, it has a restoring effect, no? And then here we have a lateral deformation symbolized by u of t or as a function of t. So not only na pamaagi no to show displacement, deformation, or the what do you call it, the position of a structure or a particle. In our lower years, we try to use the symbol S for a 1 degree system position or delta S for the displacement. And then, sa inyo na din, pag-abot na din sa projectile motion, we already try to consider no, the two-directional or the 2D. So, use the X or the Y for the position along X and position along Y if your projectile, and the displacement along X and displacement along Y is represented by this one. And then later on, after the 2D, you already consider the 3D. You have the rectangular components, lalo dahil may X, Y, and Z, and the magnitude R. So you also have the displacement Z. So this one, this is a pretty straightforward, and it is also being used here. So dili lang ato lang ginagamit is U as a function of time. So U represents the lateral deformation or deflection. Actually, we can also use no X of t. But for generalization, let's just try to use U. So yes. Okay, moving on. We have here a sample of a SDOF system or a single degree of freedom systems. So on this side, we have a water tank here. So this can be idealized no, like a lamp mass on the top with a massless column. On the other one here, we have also here a mass on the topmost and then supported by a column. Also here we have a framing which we can idealize as a single degree of freedom system. So here this is an idealized structural system. So sa may naaning a figure. So we have our idealized structural system. So if you remember no, ato lang siya i-draw as like this. And then we try to experiment. Now we try to move the idealized structural system. So again, the structural system, it has a mass on the roof here. And then the columns here that is massless, but it has a lateral stiffness K. So we try to move this SDF or this symbol structure in the lateral direction by a displacement of U naught. So when we say U naught, pasabot mo na siyang initial katong displacement. Now, after we displace it, so na siya displacement no here that is U naught. After displacing that, since the column which is flexible on the lateral direction, it has a lateral stiffness K. So same sa spring no that this is Hooke's law, katong F is equal to Kx, negative Kx. The K is the lateral stiffness of the spring. So sa spring, di ba, if you have a spring and then if nakaiibutang nga mass, si spring is mo displaced, mainat siya. But after removing the mass, the spring will return to its original position. So here, same thing also that happens now. The columns uh, will try, since the displacement is structure, it will try to make the structure to return in its neutral position. So if nakagi-apply nga force diri, it will also develop an equal restoring force that it will restore the structure in its normal or neutral position as in this second position. But since the applied lateral displacement or force is equal to the restoring, so may tabo, mura po siya mo, balik og lahos sa pika side. So igor naman siya so ang purpose man ni restoring force is mubalik siya sa iyang original position or neutral position, but since equal man sila, wala nagpugong, mura pug musayaw on the other side si structure with the same displacement nga U naught. And then naa naman po yung lateral nga kuan stiffness, it will return to its natural or neutral position this time, shown here in time 4. But since wala may resist adto, igor mo siya mo pabalik sa system in its original position, musayaw na sad siya. And then this event will happen perpetually or forever and ever. So muna siya no. This one here we have a graph. This is the lateral displacement of the roof as a function of time. So our x-axis is a function of time, and then our y-axis is displacement, that is u as a function of time. So initially this is the displacement, then at time 2, it returned to its original 0 displacement, and then at time 3, it displays on the other side, and then isayo siya pabalik, and then ibalik siya sa initial displacement until at such time forever and ever. Amen. So yan na, nahitabo. Balik-balik siya, no? There is an oscillation of the structure na walay katapusan. So this is the idealized structural system. Now, this oscillation, no? So we call this oscillation. So we have a sinusoidal graph here. This oscillation will happen forever and ever, but it will never come to rest. Now, in real life, this is unrealistic. This does not happen in real life. We know that in real life, if we try to move or vibrate something, the vibration will eventually come to rest. So what will we do with that? So what do we do with that is that we try to add an energy dissipating mechanism. Para ang atong idealized structure will become from unrealistic response, it will become at least close to realistic. So we try to add an energy dissipating mechanism. So we try to add here an energy absorbing element. So it is introduced in the idealized structure, the viscous damping element denoted by a dash pot. So nanatay ko we have a mass M here on the roof. And in the column, we have a lateral stiffness K, but with our deformation U of T. And then we added the energy absorbing element symbolized by this one. It's a dash pot. So it's a coefficient or damping coefficient as a symbol of C. So this becomes now our functional elements of a single degree of freedom system. So eventually, hinahinay. So from the previous example, no, perpetual yung motion nga balik-balik, by the application of the energy damping system, our graph will eventually, or the displacement will eventually come to a stop. So in our structures or buildings, no, if there is an earthquake or lateral or vibratory ground motion which causes lateral displacement of the structure, so we that there is a damping mechanism, no, that happens on the structure. More likely, this is due to the friction. So it will eventually cause the structure to stop vibrating and until it will rest. So tanong lang sa nato ni balik no kanina nasa idealized structure na to. If you notice no natay mga hidden lines here. These hidden lines denotes the displaced structure, displaced column. Then this one, the displaced damper. Okay, hold on the equation of motion. So we have what we call an equation of motion. So what is this equation of motion? So the equation of motion describes the behavior of a physical system. So mano siya ang kuan. Main definition ng equation of motion. It describes the behavior of physical system in terms of its motion as a function of time. So in engineering no and physics, we try to describe an object mathematically. No, we try to form equations for that one para mas masabtan na to siya. So that is in physics or in engineering. So more specifically, equation of motions describe the behavior of physical system as a set of mathematical functions in terms of dynamic variables. So muna siya no nga, like in your lower years sa inyong dynamics of rigid bodies, you try to describe the motion of a particle like in the projectile or the other one. You di ba natin mga formula like the final velocity is equal to the initial velocity plus or minus the acceleration times the time, at etc. So that is the description, or we try to describe the motion in terms of its position, velocity, acceleration, and etc. So there are two main descriptions of motions. We have the kinematics and the dynamics. So sa kinematics, no, this is the simpler one. So this is the sa may consideration diri, di ba? This is we try to consider we have the constant acceleration, or probably there's no constant acceleration, and then dali na po siya i-solve through integration or differentiation, direct integration or differentiation. So here we try to derive the positions of object and time. So mo to siya dili di ba in your dynamics of rigid bodies, you have the displacement or the position. What else? You have your initial velocity, v naught, final velocity. What else? You also have the consideration of the acceleration and the time. Now, in the dynamics, as in like the structural dynamics this time, uh, this is in general, we try to describe, we include the moments, no, the momenta, forces, and energy of the particles are what are taken into account. So, mo din siya si dynamics. So sa dynamics, no, we try to use here differential equations to describe the motion of a particle. So here sa ato ang single degree of freedom nga system, we'll be trying to use the differential equation to describe the motion or to have an equation of motion sa ato ang system. So we try here to use differential equations that the system satisfies. So we try to use concepts of Newton's second law or D'Alembert's principle, Euler-Lagrange equations, and etc. So, diba? So again, so in the dynamics we have the consideration of the differential equations at ang calculation for the equation of motion. So since there is a differential equation of motion, so it is usually identified as a physical law at the time the definition of physical qualities. So since we have an ODE here or a differential equation for the equation of motion, when we try to solve that one, we will have a general solution with arbitrary constant, kay general solution man ta. And then by applying our initial condition or initial boundary or initial values, we will obtain a particular solutions. So mo siya ang dagan sa ato ang differential equations na equation of motion. So our equation of motion no, for this one is we derive it from as a function of the position. So but no, in general, the equation of motion is a function. So this is the equation of motion is a function of the position. I mentioned earlier no nga, equation of motion is a function of the position r vector of the object. So yung anong r man? So if nyo madumduman no sa inyong dynamics of rigid bodies, no, if we consider a three-dimensional na system, let's say we have our x, our y axis, and the z axis. And then let's say there is a particle on this side. So how do we describe its position? So the position of this particle is described depende sa iyang direction along the x. So we have a position here along the x. It has also a position along the y or a position along, let's say, z. So malo siya sa rectangular components. And then its magnitude no, from this point paingon ani that is symbolized as the r. Now in structural dynamics, we will try already to consider the position as a vector. So since ito mong gina-consider sa equation of motion si position, and then we also try to consider its velocity. So again, the velocity vector is equal to the first derivative of the position vector with respect to time. And then its acceleration. So the acceleration vector is just equal to the second derivative of the position vector with respect to time, or the first derivative of the velocity vector with respect to time. So it then, the equation of motion di, we take into consideration the position as a function of time, the velocity is a function of time, and the acceleration as a function of time, and the time itself equal to 0. So, ay mo kalibugan nga nun sa maning na dot and then double dot sa ibabaw. So, mura na siya kuhan, di ba? If we have our position with respect to time, and then if imo na siya i-differentiate, di ba natay prime notation like r prime of t and then r double prime of t. So, another notation is we can use the derivative is kanang na dot, na uh, r dot t, and then we also have r double dot t. And then we also have the likeness notation katong dr over dt and d squared r over t squared. So, ano mo kalibog anak? So, the single dot here represents the first derivative of the position r with respect to time. And then the double dot r here symbolize or shows the second derivative of the position with respect to time. So, muna siya si acceleration, and then this one here is the velocity. So here, no, since if we try to involve the differential equation here, and then so you will have a general solution, and then you will have your particular solution. So the initial conditions give ginatanaw na to, so we can have a particular solution is to determine the position when time is equal to 0 and the velocity at time is equal to 0. And then eventually, you will have a particular solution. Sometimes the equation will be linear and is more likely to be solvable. Yes, at times it's linear and then the equation is solved. The motion of the idealized one-solid structure caused by the dynamic excitation is governed by an ordinary differential equation called the equation of motion. So, mo siya. The idealized one-story, its motion is described or shown by the equation of motion. And then that equation of motion is an ordinary differential equation. Formulation of the equation is possibly the most important phase of the entire analysis procedure and sometimes the most difficult part. Yes. Sometimes equations will be linear and is more likely to be exactly solvable. Other times, this will try solve. So the equation of motion can be determined using the following approaches. We have the first one, the direct dynamic equilibrium approach. And then the second one, we have the principle of vertical work or energy method. So we'll discuss this one in our next video.